let's first, I'm just going to rewrite the first fundamental theorem of calculus, and we'll kind of compare, contrast the two. Let's see, it was the integral of f prime from a to b. And again, it's like this awe-inspiring fundamental theorem that sure seems to make sense. If you integrate a derivative, you get back to where you started. You get back to the original function. Is that really all that intriguing? That if you integrate a derivative, if you antiderivative a derivative, you get back to the original. We need to be a little bit careful either with C or with limits, with f of b minus f of a. So it's not just f of x. You either have the plus c at the end, or you have f of b minus f of a, either one. And then, sort of review here, evaluating that, there's at least 3 different ways to evaluate it. Probably our favorite way is with the calculator in Math 9, right? Because then the calculator just does it all for us. We can take antiderivatives by hand. That was on the test last time, and it's what we'll do starting next week. I've got 3 days of antiderivatives by substitution. We don't really know what that means yet, but there's a lot coming, obviously, antiderivatives by hand. And then we can also use area under the curve, if they give us a curve, and if it's a nice geometric formula. Or sometimes they just tell us what the area is. So like it's not a nice shape, it's just the area of that's 7. Like, okay, that makes the integral easy. You just told me what the answer is. So first fundamental theorem, integral of the derivative gives us the original. But there's a couple different ways to do that depending on the problem. If it's crazy hard, we'll give you a calculator. If it's power rule stuff, we'll have you do it by hand. Or we can just give you a picture and you can find the areas under the curve. Second fundamental theorem of calculus. So it's a little bit same idea, just kind of reversed. First fundamental theorem was integrate a derivative. The second fundamental theorem is the derivative of an integral Well, if you integrate a derivative and get back to the original, what do you think happens if you take the derivative of an integral? Integral and derivatives are, you get back to the original. We're kind of just going on this on our little chain, our progression here. So first fundamental theorem is if you integrate a derivative, so you take a derivative and then you integrate it, you're back to where you started. The second fundamental theorem is if you take the derivative of an integral, so you integrate and then you take its derivative, you're also back to where you started. But we need to be careful on this one because just like integration, the big thing with integration is don't forget the plus c. The big thing with taking a derivative my face is hiding it now. It was why we have this Tootsie Roll pops up here the whole time, so that you won't forget to do the chain rule. So just like when you integrate, the big thing is don't forget plus c, or make sure you get your upper and lower limits right. The big thing with second fundamental theorem, taking a derivative, is don't forget the chain rule. All right, I'm going to show the complicated thing first, and then we'll see that these problems are a lot easier than this complicated thing is going to make it look. Like, well, you're not going to have to worry about the complicated thing, but I want you to see where it comes from. So we're going to take the derivative of an integral. That is a u. The u is playing the role of the pink triangle. Remember the pink triangles, that with chain rule stuff. We're going to chain rule off that u here in a minute. F of t dt. You got all kinds of letters going on here. So x we're familiar with. U is another function that we'll have to chain rule in a minute. A is a constant. So 12 or pi or 37. T is kind of just a placeholder, like f of x, but we're already using x, so we're going to use f of t. All right, well, d dx is still there, right? We got to work from the outs or from the inside out. So d dx, we haven't applied that yet. Let's work on integrating. And here's where maybe this is helpful. If we integrate f, we get uppercase F. Yeah, if we integrate little f, we get big F. And then we need to evaluate at the two limits. It's okay to giggle right there if you think that's funny. But it's pronounced f of u, right? You got to include the of there so we're not in danger here. F of u minus f of a, because the integral of little f is big F. But now we're going to do the derivative of big F. Well, derivative of big F is going to be back to little f. So this is going to be f of u, but we have to chain rule off the u, so du dx. Now remember that a was a constant, so that means f of a is some constant. And what's the derivative of a constant? 0. So that part would go away. So here's the deal with this next test. Some people, they're going to go the long way around on some of these problems. They're going to actually take the integral and then take the derivative. But the deal is we want to use the shortcut and skip that step and just go straight to the answer. That's what we want to do. Again, I think this is a lot easier than it sounds in the explanation. Let's do an example problem. So d dx of the integral. So already we should be thinking, wait a minute, those two things undo each other. Those are opposite things. So this should be, in some ways, an easy problem, because we're just going to cancel each other out here. From 5 to 3x squared of t sine t dt. I don't want to, and in fact I can't, take the integral of t sine t. I don't know what that is. But I do know that once I take the integral of it, I will take the derivative of it, and so that'll get me right back to where I started. So if you kind of follow the pattern, we're going to have t sine t, but instead we're going to plug in the top limit for both of those. So 3x squared sine of 3x squared but then we have to, don't forget the chain rule. So the chain rule from 3x squared is 6x. And yeah, we could clean that up if we wanted to, but we're really embracing this safe stop thing and just leave it alone. Safe stop that. So there's a lot of theory going on in the background, the integral of the derivative, but in practice it's like, well, they cancel each other out, so I'm just going to plug in the top limit and multiply by its derivative. Let's do another one. I'm going to set this one up a little bit differently, but it's the same thing. Find the derivative of h of x equals the integral from x squared to 3 natural log t cubed dt. These are fun problems for calculus teachers to write because you can make this as hard, as crazy, as complicated as you want. It doesn't matter because you're not really doing anything with it. You're not actually taking its derivative or its integral. Well, I guess you're doing both. They cancel each other out. So you don't have to worry about how complicated that thing is. I'm going to write it in the format that we had it. So I want the derivative of the integral that step's not absolutely necessary, but it helps me see that I'm taking the derivative of an integral. So this is a second fundamental theorem of calculus question, the derivative of an integral. Except how is this one different than, we've only seen one example, kind of two examples. What's different about this one? The constant's at the top. And that matters, right? Because you're supposed to do the top one minus the bottom one. Is there a way I could is there a way I could like flip those? Yeah, make it negative. In fact, I don't have to worry about I could make the ln negative. I could put the negative all the way out front though. So I am going to flip those. And the only price I have to pay is to make the thing negative. So I want the constant in the bottom so that when I subtract it off, it just goes away. I don't have to worry about it. I suppose you don't have to flip it as long as you remember where it comes from. This would be 0, so it'd be 0 minus whatever this one is. So you could avoid doing this as long as you remembered that it's top minus bottom, so you're going to end up with negative. All right, from here it's just plug in the top one and multiply by its derivative. So the d dx and the antiderivative kind of cancel each other out. So natural log of, the negatives needs to be there. Natural log of x squared cubed times chain rule 2x. And again, you could clean that up if you wanted to, but why bother? Let me give one for you to try, and you can get started on the homework. Find the derivative of the integral from sine x to negative 12 of e to the 5t dt. Again, that looks crazy the first time you see it, but we now know the secrets of these problems. So try that one and then we'll go over it. So e to the 5 sine x times the derivative of sine x, which is cosine x. Whoops, left off the negative sign. So again, the problems look really complicated, but they're not that hard. So your assignment is Finish those last 4 off the worksheet that we kind of started, and then the assignment that goes really fast is this worksheet. So 20 minutes left, 15 minutes left. You can probably still finish at least this worksheet.